enjoy that. Yeah, that's right. So we won't be here next week, but we still got this week to get through. So let's see. We want to get as far as we can into the notes. So I posted some new homeworks, right? This goes through actually the end of spring break week, which is Saturday, March the 19th, right? So when you get into spring break, be careful to note that this have a homework due right at the end of spring break. And then there's one I've got scheduled for Thursday. This is, Emil was asking me, how's this different from the trig homework that you just did? Well, this is just finding trig functions of angles using reference angles, right? So this is finding trig functions of angles for angles that are not acute angles. So I don't know if there are any, I don't think there are right triangle problems in this homework. There might be some, but that's not the focus of the homework. It's just computing sine, cosine, tangent, etc. for angles that are either negative or bigger than 90 degrees using reference angles. Obtuse, yeah, well, obtuse is bigger than 90 degrees, right? Okay, so that's the opposite of acute. Well, anyway, so that's the current homework list, right? So notice this one is due fairly quickly, but most of these problems are easy. Okay, they're pretty short because it's just here's an angle, find the reference angle, and then find sine and cosine or whatever of that angle. Okay, it's pretty straightforward. Now, the one thing to be careful of is unless it asks for a decimal approximation, right, in the homework, be sure you give exact values. So that's been tripping up people throughout the semester on the homework. Okay, so when I say exact value, decimal is not exact. Okay, students sometimes have this misperception that if I have a lot of decimal places, that must be exact. No, that's still an approximation. Okay, exact would does not usually involve decimals. All right, so for instance, if the sine of an angle turns out to be square root of 3/2, and many times it will, then you want to type in square root of 3/2 in your homework, right? That's the exact answer, not the decimal approximation for square root of 3/2, which I think we saw last time was 0.86 something, right? Okay, so be careful about that in the homework. All right. So do you guys have questions? Is there anyone else who did not get their written test back? Okay. All right. So if you're in that boat, then see me when we take a break here and I turn the tape off. Remind me in a few minutes here to start the roll sheet, right? Okay. We do have something to do here to start with. So speaking of reference angles, so I have some recall for you. That line's not supposed to be there. So I have two angles here. I want you to try here sketching these angles. I don't have any more graph paper, so you'll have to do this in your notes. Try sketching these angles, just a rough sketch of the angle, right? And then I want you to find the reference angle, right? The reference angle that's associated with that angle, right? Okay. So remember, the reference angle is going to be always between 0 and 90 degrees, right? It's going to be an acute angle. So so draw the angle first and then find the reference angle. That's a bar there above theta, right? So then you have the angle theta and then find theta bar, right? And then once you found theta bar, then see if you can the sine and the cosine for theta. Okay. Now, actually, you can do this, these two, just in your calculator, right? You can find the sine and cosine, right? But the calculator is going to give you a decimal approximation. So, especially for this one, see if you can find the exact value for the sine and cosine, right? Not giving me a decimal approximation. Here, on the other hand, this is not a special angle. 400 minus 460 degrees is not a special angle. So you're going to have to ultimately use the calculator anyway to find the sine and cosine. So you'll have to give a decimal approximation, but try to find the reference angle first. Okay. All right. Now, just one other hint. Okay. Remember, 2 pi, which is 1 revolution, right? In radians, 2 pi is 1 revolution. That is the same as 12 pi over 6. If you convert that to 6, okay, 12 pi over 6 is 2 pi, right? So keep that in mind. That's helpful when you're drawing 23 pi over 6 to remember that, 1 revolution is 12 pi over 6, right? So you can already see you've got more than 1 revolution in that angle, right? That you're going to have to count for when you're drawing it. Let me lower the screen. So you guys at home too, also, right? Because I may ask one of you to tell me what the reference angle is. And then it's pretty easy from that point to find the sine and cosine. That's the point of finding reference angles, is to simplify the process of finding sine and cosine, right? For these more difficult angles, right? Always go 90 degrees, but 0 and pi is possible. This is how okay, and you did. Remember, positive angles are on counterclockwise, right? Well, it's 0 and 9, or it could be 0. That's not. Yeah. Yeah, it's that's so. So do that. And yeah. So Six. All right. Let's see how we did here. Okay, so who answered me there? Oh, Ahmad. Is it 690? I don't know. Is it 690? I wasn't thinking in 23 pi over 6. I wasn't thinking in degrees. Okay. Kenneth says yes. All right. So but let's try to do it without let's try to do it here without thinking in degrees. Let's try to stick to radians here for a second. So I already mentioned there that 2 pi was 12 pi over 6, right? So you know in 23 over 6, that in 23 pi over 6, you have one full revolution already, right? Because that is 12 pi over 6. Now, if you went 2 full revolutions, right? Keep in mind you're going counterclockwise. That's the positive direction for angles, right? So if you went 2 full revolutions, you would have eaten up how much in radians? 24 pi over 6, right? But we didn't quite get to 2 full revolutions, right? Because we stopped at 23 pi over 6. So that means we have to stop over here in the 4th quadrant, right? We're going to stop just short of 2 full revolutions. And now to find the reference angle, remember the reference angle is the positive angle between the terminal side and the x-axis. So here's your terminal side that we just drew, right? So if you draw in a positive direction up to the x-axis, that's going to be the reference angle. And how much is that? We can see now that's what? Pi over 6, right? Because that's what was left, right? From us going, that's what kept us from going 2 full revolutions, right? Was that that extra pi over 6, right? So our reference angle for the original angle is pi over 6. And see now, you supposedly you have memorized sine and cosine for pi over 6. I hope so. Okay, or you have some way of remembering what the sine and cosine were for pi over 6. So see, that allows you now to compute the sine and cosine for 23 pi over 6, right? Just based on your knowledge of pi over 6. That's the point of reference angle. So so if we were going to compute the sine of 23 pi over 6, we know that is going to be almost the same as the sine of pi over 6, right? Except we may have to adjust the sign in front, right? The plus or minus. And in fact, here we do have to adjust it, right? We have to change it to negative because we know this angle 23 pi over 6 is it ends up here in the 4th quadrant, right? But in the 4th quadrant, the sign is negative because the y-axis is negative in the 4th quadrant. So so we write down minus sine of pi over 6, and now we have to remember what that was. Was that 1/2? Yeah, okay. So now you've got the exact value for sine of 23 pi over 6. Now, if you did that on your calculator, if you entered 23 pi over 6 and punch sine, the calculator would tell you minus 0.5. And minus 0.5 would also be exact in this case because 1/2 is exactly the same as 0.5, right? Okay. So even on WebAssign, you could get the answer right here for the sine of 23 pi over 6 without, just from your calculator, right? But cosine is a little bit trickier, right? Because cosine of 23 pi over 6 would be the same as the cosine of pi over 6. And again, we have to adjust the sign in front. But in the fourth quadrant, cosine is positive because the x-axis is positive, right? In the fourth quadrant. So we don't have to change the sign here. We just get cosine of pi over 6. And what is the cosine of pi over 6? Yeah, that's the square root of 3 over 2. And in your calculator, as I mentioned, right, you will get, the calculator would say, the cosine of 23 pi over 6 is something like 0.86, right? And but that's not exact. The exact correct answer is square root of 3 over 2. Okay. So if WebAssign asks for an exact answer and you typed in 0.86, it's going to count you wrong, and then you're going to go crazy and email me and say, "What am I doing wrong?" Right? And the answer is, well, you're not really doing anything wrong per se, but you're just not entering the answer as it was asked, right? Okay, what about minus 460? That's not a special angle. So so you really do have to rely on the calculator. So finding the reference angle in this case is not as helpful because you still have to use the calculator to find sine and cosine here, even after you found the reference angle. Well, you could have used the calculator right from the beginning, because the calculator will certainly accept input of minus 460 degrees, right? As long as you change the calculator to degrees first. And what does the calculator say the sine of minus 460 degrees is? Negative point what? Approximately. Okay. So minus 0.98. All right. But let's go ahead and find the reference angle here. So we want to draw this angle in the negative direction, right, guys? In the negative direction. So that means it's going to go clockwise. So when you draw that, you'll draw clockwise 1 revolution. That's minus 360 degrees. And now you've got another minus 100 degrees to draw, right? So that would put you a little bit past 90 down here, right? Okay, but only 10 degrees past the 90. So I think our angle is going to look something like that, right? So it's going to end up there in the third quadrant. And what's the reference angle going to be? Not this angle, right? Okay, it's going to be the positive angle between the terminal side and the x-axis. So it'll be this angle here, okay? Let me draw it positive, not negative, because the reference angle has to be positive. So what is that angle? Yeah, it's 80 degrees, right? Because we went 10 degrees here into the third quadrant, correct? In drawing the original angle. So the reference angle is 80 degrees. So we know that the sine of minus 460 is also the sine of 80 degrees, except we have to adjust the sign in front. And again, we have to change that to minus because in the third quadrant, sine is negative because the y-axis is negative in the third quadrant. What does the calculator say the sine of 80 degrees is? I bet it says it's 0.98, right? Yeah. And then, of course, you changed it to negative, right? So, of course, you get the same answer either way. So cosine of minus 460 degrees is the same as the cosine of 80 degrees. Not quite, because in the third quadrant, cosine is negative, so we have to put a minus in front of that. And now you just punch in the cosine of 80 degrees and change the sign, but you could have just punched in the cosine of minus 460 degrees to start with, right? Okay, so in this case, the reference angle is really not saving you time, okay? Because you're not going to find the exact answer in any case. You have to rely on the calculator. What is that approximate? Negative point what? Negative 0.17? All right, let's try something here. As one more reminder from something that we did last time. Remember, remember the Pythagorean identity from last time, which we talked about right at the end of class. And remember that Pythagorean identity said, if you take the cosine of an angle and the sine of the same angle, square those and add them together, what do you get? What? One? One, yeah. Okay. So this is called the Pythagorean identity. Very useful identity. Okay. So remember, it's not sine theta plus cosine theta. It's sine squared of theta. So take the sine of an angle, square that value, add in the cosine of the same angle squared, and that should add up to 1. Let's see if that works in this case. Whoops. All right, let's see if that works in this case, because we have sine and cosine, right, of minus 460 degrees. So the sine was minus 0.98, right? But remember, we're going to square that. And the cosine was was that minus 0.17? Yeah, minus 0.17. And we're going to square that also. And does that turn out to be approximately 1? Try that on your calculator. Is it 0.999 or something? What? 99? Okay, yeah, right. So that's just an example there of the Pythagorean identity. We didn't get exactly 1 because we had rounded off the 0.98 and the 0.17, right? Okay, so when we squared them and added together, we didn't get exactly 1, but if we had the exact value for the sine and cosine of minus 460, gotten exactly 1 from this equation. You remember the other Pythagorean identity? There's 2 of them. Yeah, it's secant squared minus, I think it's this, tangent squared equals 1. Okay, so that's the second Pythagorean identity, but this one is far more famous than this one, but they're both quite useful. All right, okay, so you do use both of them from time to time. Okay, but this is certainly a lot more well known than this second Pythagorean identity. Okay, y'all did pretty good there on your reference angle. That's what the homework is all about. All right, so computing these reference angles and then using that to compute the trigonometric functions, sine, cosine, tangent, etc. of angles. Now, there is one other thing in the homework that's kind of a little bit of a special topic. It's just sort of thrown in there for fun. Kind of an application of trigonometry again, all right? But it's not in the prior homework. So it's another formula for area of triangle. And we already had a formula for the area of a triangle that we learned way back at the beginning of the course. Remember, at the beginning of the course, we actually kind of proved, right, that the area of a triangle is 1/2 of the base of the triangle times the height of the triangle. Okay, so remember the base was you had to think of drawing the triangle with one side horizontal, and that horizontal side was the base, and then the distance from that base to the top of the triangle when it's positioned in that horizontal position, that's called the height of the triangle. So if you take 1/2 base times height, that gives you the area of the triangle. Okay, that formula is sometimes a little bit awkward to use, though, because you have to be able to compute the height, which is not always easy to do. Okay, all right. So that sometimes limits the usefulness of this formula for finding the area of a triangle. I have another actually 2 other formulas I'm going to show you here today, but one of them is included in the homework, so that's the one we want to focus on. I'm just going to show you the other one for fun. So here is another formula for finding the area of a triangle. It kind of looks like this formula, but it's just slightly adjusted. So if you're given a triangle, it can be any triangle. It doesn't have to be a right triangle. if you're given any triangle and you know two sides of the triangle, and you know the size of the included angle, that's the angle between the two sides that you know, okay, then this formula will also give you the area of the triangle. So it's 1/2 times the product of the sides, and then times the sine of that included angle. It has to be the angle, though, between the two sides that you know, okay? All right, so it couldn't be this angle here or this angle down here. It has to be the angle between the two sides that you know. And again, this formula works for any triangle. So this angle does not have to be acute. It doesn't have to be between 0 and 90 degrees. Kind of looks like in this picture, right? It's bigger than 90 degrees, right? So does not have to be a smaller angle. Let's apply that just briefly here to this picture. And then there's a couple of problems in the homework where you're asked to use this formula. So just keep in mind that formula when you encounter the homework problems. And since we're so good at computing sine now, right, it makes the formula easy to use. So it says the ancient game of Pell is played on a triangular field where each side of the field is 70 meters, okay? And so we want to find the area of a Pell field, okay? So in Pell, the field is, this is an equilateral triangle, okay? It's an equilateral triangle. So the lengths of the sides of all the sides of this triangle are 70 meters, and then the angles are all 60 degrees because this is an equilateral triangle. So all the angles are the same. So that means they all have to be 60 degrees, right? So let's see if we can find the area enclosed by a Pell field. That's probably a pretty big area, right? Because these sides are all 70 meters. So to play Pell, you have to have a pretty decent space, right? Okay. Have y'all ever played Pell? Yeah, there's no game of Pell. I just make this up. Okay, so it's just a fanciful problem on my part. Okay, sounds kind of convincing though, right? So okay, all right. So let's calculate the area. We can make our own game, I guess. So we should think about what rules we want for Pell. But we have played on this size field. Okay. All right. So what would the area be? Well, according to our simple formula, right? It's going to be what 1/2 times what the sides, right? A and B, and we can pick what sides here we want to call A and B. It doesn't really matter since they all have the same length, right? So let's call this one A, and let's call this one B. And then, of course, we know what the included angle is, right? It's 60 degrees because all the angles in this equilateral triangle are 60 degrees. So we have 1/2 times 70 times what? The sine of 60 degrees. Okay. And so now this is very easy to calculate, right? So we have 1/2 times 70 squared times, and what is the sine of 60 degrees? So that is a special angle. So we can compute this exactly. It's what? Is it square root of 3 over 2? Yeah, okay. So square root of 3 over 2 there. So exactly what do we get? Well, we get, is this 4,900 times the square root of 3 divided by 2? And I guess you can divide 4,900 by 2. And oh wait, no. Yeah, okay, right. Yeah, 4,900. So, and then 4,900 over 2 is what? Is that 2,450? Okay, yeah, 2,450, I think, times square root of 3, right? So there is the exact area of there's the exact area of a Pell field. Y'all don't look convinced. Is that right? Yeah. So, well, this is how WebAssign wants you to do it. Okay. So I'm a little bit more forgiving than WebAssign on tests, especially, but WebAssign doesn't tell you. Well, I don't. Usually, WebAssign does not say anything if they want it in exact form. They will say if they want it in decimal approximation, but if they don't say anything, that means exact form. Okay. Yeah, so this would be exact form. Well, so this formula for triangles at least has the advantage that you don't have to compute the height, okay, of the triangle, which sometimes is tricky. But you do have to know the size of the angle, right? Okay, and then you have to be able to compute the sine of the included angle. That's not always so easy, especially if you don't have a calculator, right? So so this formula also has its limitations. There's another famous formula for the area of a triangle. This is called Heron's formula. So this is named after a Greek mathematician Heron. So this is an ancient formula also. And so now you got three formulas for the area of a triangle. Here's how, and the advantage that Heron's formula has is that you just have to know the lengths of the sides. Don't have to know anything about the angles. You don't have to calculate height. Just have to know the lengths of the three sides. Okay. Now, in this formula, so the way this formula works is it's a square root of a big product. The A, B, and C are the lengths of the sides. All right. So that's kind of obvious, right? Now, this quantity S, though, is I have to explain what that is because you do have to compute this first, okay, before you can use Heron's formula. This quantity S, though, is what's called the semi-perimeter. Semi-perimeter of a triangle is just half the perimeter of a triangle. Okay, perimeter means the distance around the triangle, right? Okay, so semi-perimeter is just half of that. So just calculate the distance around the triangle, which of course you can do just by adding the sides together, right? And then just take half of that, and that's the quantity S. Let's see how this works out for. I didn't try this, so let's see if Heron's formula agrees with what we just did, right? So let's apply Heron's formula to this triangle, to our hypothetical Pell field, right? And see if we come up with, wow, you're going to tell me with this one, it doesn't look like it's going to be the same, does it? So I'm curious now. So, all right. So first, to use Heron's formula, we have to calculate the semi-perimeter. So you just calculate the perimeter of the Pell field and divide it by 2. So, well, the perimeter of the Pell field is kind of obvious, right? It's 70 plus 70 plus 70, which I think is 210, right? Divided by 2 is 105. Yeah. So the semi-perimeter here is 105. Let's write that down. So the semi-perimeter is 105. So we get square root of 105 times, and then you subtract all the sides from the 105. So you have 105 minus A, which is 70, and then of course 105 minus B, which is also 70, and then you have 105 minus C, which is also 70, right? So you come up with this big square root. Wow. So that looks like the square root of 105, and then 105 minus 70 is 35, right? So you have 35 cubed, okay? What is that number? Oh, no, just under the radical. I'm sorry. Yeah, the quantity just under the radical is what's 105 times 35 cubed? It's going to be a big number. Okay, say that again. What? 4501875. Okay. Does that divide by 3? You'd be hard pressed to know that without having some prior knowledge, right? But it does divide by 3. What is the product? 1500 what? 625 times 3, right? And the reason I wrote it like that is because go away news. How do I get rid of this? Okay, yeah. 1500625 I think is a perfect square. And what's its square root? Is it 2450? Yeah. What? Yeah, square root of the big number, right? Yeah. 1225. Oh my God, this thing. Stop. So what did we do there? Fishy. Oh, it already came up. Oh, okay. All right. These two are, well, obviously then we've got some sort of something fishy going on here, right? Okay. So either I wrote down Heron's formula wrong, which I don't think so, or we made some other miscalculation here, right? Because these two, yeah, those two should agree, right? Oh, I know what I did. Oh, I know what I did. I made a miscalculation up here. Y'all let me do that. See what I did wrong? See, I had 1/2 here, and then I had this 2. So I was supposed to multiply those. So what is this denominator supposed to be? 4. Oh, yeah. So I was supposed to take the 4,900 and divide by 4, not by 2. Oh, so that gives me indeed, what y'all told me there, 1225? Yay. Okay. Oh, thank God we found that. Okay. So the proper area was 1225 times the square root of 3. And so this is correct, right? The square root of 1500625 is, as y'all were telling me there, this, right? 1225. Yeah. Okay. So, oh, we do get the same result. All right. Okay. So, well, let's not try it this way. All right. So, but we could do that pretty easily for this Pell field, but we don't really. But anyway, there are 3 formulas, right, for areas of triangles. Yeah.
So what did you
This is the only one I know that has a name. This is called Heron's formula. Yeah, like it's just like the bird, but it's not named after a person. Okay. These two, as far as I know, don't have names, but they probably do. All right. Okay. I just am not aware of them. No, in the, well, you know, if you're trying to compute the area of a triangle, right? I mean, you have somebody that works, you'll compute the area of a triangle, and then you'll use it for whatever purpose you need it, right? Okay. I was just pointing out that these formulas have some advantages and disadvantages, right? So that's why we have so many different formulas, and there's probably more, so many different formulas for areas of triangles, because some of them are easier to use in certain situations than others. The advantage of Heron's formula, though, is it just involves arithmetic, right? It doesn't involve, for instance, trigonometry at all. Okay. It's simpler in the sense that the operations involved are not advanced, right? So you could teach this to grade schoolers that have to know what square root is, right? But this involves knowledge of trigonometry, right? Okay. All right. Okay, so last time we were looking at, it's not in these notes, but remember last time we saw the sine curve. I think I have a picture of that maybe here somewhere. And we at the end of class, so there it is, right? There's the graph of the sine function. So here we have the x-axis marked off, not in degrees, right, but in radians. And so if you compute the sine for different radian values, right, and graph it, you get this curve. Okay, so this is the graph of y equal sine of x, again where x is measured in radians. And so you get this nice oscillating curve, right? Okay, which is very useful in practice. And but what this does remind us of is that the fact that when we're setting curves that aren't straight lines, okay, we very quickly run into curves that have lots of wiggles in them, right? Lots of oscillations in them, lots of waves in them, like the sine curve does, okay? And so we need to develop some terminology that we can use to talk about curves like this, right, that have lots of oscillations or wiggles, all right? And so that's what we're going to do right now, is to first just to develop some mathematical language that we use to talk about curves like that have lots of bends in them or wiggles in them, like the sine curve does, okay? So you're probably already from prior classes familiar with this terminology. So if this is a review, that's great, okay? But if you're seeing this terminology for the first time, it's very easy to understand this terminology. So we'll not find this difficult anyway, okay? So let me scroll up here to the top of the notes. So in mathematics, when we describe how a function is oscillating, or how a function is waving or wiggling, as I like to say, okay, some of the terminology we use to do that is it's called increasing and decreasing. We try to describe where a function is increasing or where a function is decreasing. Okay. Now, I have here written a technical definition for increasing and decreasing. And when you look at this, it looks like it's very complicated. Okay, but it's really not. If I explain it with a picture, it's easy to understand these this kind of technical definition of when a function is increasing, or when a curve is increasing, or when a function is decreasing, or when a curve is decreasing. You don't have to memorize these technical definitions, though, at all, to be able to use the terminology increasing and decreasing properly. Okay, all right, it's very easy once it's sort of described to you, once it's explained to you. It's very easy to understand how this this terminology works. Okay, so we always describe a function as increasing or decreasing over on a particular set in the domain of the function. Usually that set will be an interval. Okay, you know, when I mean an interval, I mean all numbers on the x-axis starting at some given value, some given initial value, and going up to some given terminal value. Okay, that initial value may be negative infinity, and the terminal value may be positive. All right. So we always talk about a function increasing or possibly decreasing with respect to an interval in the domain. Okay, or as mathematicians we would say over or on an interval in the domain of the function. All right. So how do we decide if a function is increasing? Okay. All right. Look at this particular picture. So here's just some function that I've drawn. So it actually this is the formula for this is the graph of x squared plus 4x minus 1. Okay, but the formula there is kind of not meaningful to us. All right, it's the graph that that we're interested in. All right, so we say a function is increasing if when you increase x, all right, when you increase x, the y values, the output values also increase. All right, so look here on the right-hand side of this curve, right? So I picked out a couple of x values along the x-axis, right? And so I just, these are arbitrary values that I picked out. So I just called the first one x sub 1 and the second one x sub 2, right? And notice then that, so here's x sub 1, right? And let's see, what's the y value that matches x of 1? Well, that's down here, right? So that's f of x of 1. And here's x2. What's the y value that matches x2? Well, that's up here, right, on the graph. So that's f of x2, right? So notice that x2 is bigger than x1, right? When you move from x1 to x2, you also increase the y values as well, right? In other words, the curve is going up. Okay, so if the curve is going up as x increases, in other words, as you move from left to right along the x-axis, then we say that piece of the curve is increasing, right? So what piece of this curve is increasing? Yeah, that's right. It starts increasing at this point, correct? Right? Okay. This part of the curve is increasing. Remember, you're always thinking of moving in the positive direction on the x-axis. You're always moving left to right in x-axis. So starting here at this point on the curve, which happens to be -2, -5. If you plug -2 into this formula, you'll see the matching y value is -5. Okay. Starting at this point, right, as x is increasing, right, the y values are also increasing as well, right? As you're going from left to right on the x-axis, the y values are also going up. So that piece of the function, that piece of the curve, we say is increasing. All right, so it's just that easy, right? So let's write that down. Somehow I've got get the touch turned off here. If I get rid of that thing. Okay. So let's write that down. So in mathematical terminology, we would say the function f or curve or the function f is increasing on or over this interval. Let's see. So, and we're describing an interval in the domain. Okay. So in the domain, where does this increasing behavior begin? You told me at this point. So what's the x value where that for that point? -2, right? Okay. And where does that increasing behavior end? Well, apparently it never ends, right? Okay. This curve is going to continue going up. So this behavior extends to what? Infinity, right? So you could put in infinity. That's just the way you write it down, just that simple, okay? The function f, I should have put the function f here first, is increasing on this interval. Now, there's some controversy about whether you should include the boundary values of the interval in the set where the function is increasing. I always include them, but not everyone does, okay? So there's not an agreement among mathematicians about this question, okay? So I always like to include the boundary value in the interval, but you don't have to be. Obviously, you can't put a square bracket beside the infinity though, right? Okay, because that's not really a number. All right, now, what's happening over here on the left-hand side of this graph? Well, notice things are opposite, right? If you pick out two x values, right, one larger than the other, and find the matching y values, right, as you're moving from x1 to x2 over here on the left-hand side of the curve, right, as you move from one x value to a larger x value, let's say x1 to x2, what's happening to the y values here? Yeah, they're going down, right? They're falling, okay? So this part of the curve, quite clearly, right, is decreasing, all right? Because as you move from left to right, the curve is falling. Remember, always, we have this Western bias here, right? We're always moving from left to right, okay? So if we move from left to right along the x-axis, right, at first the curve is falling, it's decreasing, and then it starts increasing, right, on the right-hand side. So the way you just write that out in words, you would just say the function, or you can say the name of the function, or you can say the curve. It's fine also. So where does it start decreasing? Apparently at minus infinity, right? We really can't see all the way to minus infinity, but I think it starts at minus infinity there and then goes up to -2, correct? And I just always put a closed bracket there at the boundary value. Okay. Now, obviously that point -2, -5 is a special point on the curve. Okay, right? So clearly that point has special significance on this curve, correct? Just like these points have special significance on the curve. What are these points called, by the way? Right here and right here. Those are the x-intercepts, right? What's this point? It has special significance on the curve. That's what the y-intercept, right? Okay. This point also has special significance. I call that a turning point, all right? Because that's where this function is switching from, in this case, decreasing to increasing, okay? In other words, the curve turns there at that, turning point, all right? It changes direction at that turning point. Yeah, Jen. I'm pretty lenient about that. Okay, I'm always, I don't know. So you have to try on the homework what WebAssign wants. I've never had, okay, so I don't have people complaining about this. Shall we try it? Let's try it. Because that's going to be the very next homework. So let's open it and see. I haven't had people in prior semesters complain about this. So either they figured it out and just didn't ask me, or it took it. All right, let's see what it says here. So here's a pretty gnarly function. All right, so there's the formula for it. It's f of x is 2x cubed minus 3x squared minus 12x. So that's definitely not a straight line, right? Okay, you can see that from the formula because you have x raised to a power higher than 1, right? So you know you're not going to have a straight line. And in fact, since x is raised to a fairly high power here, 3, really actually end up getting a kind of a twisty curve, right? Okay, so one of these has to be the right answer. Okay, now which one is it? I wonder. All right, now here's what you can do to find this out. Okay, you don't have to try graphing this by hand to figure it out. Okay, because in the homework I have given for you a link to a graphing device. All right, but you can do this also on your graphing calculator if you have a graphing calculator. I'm afraid if I open this, well, let's see what happens. All right, so did anyone see what the formula was? Let's go back. Okay, someone write this down for me. All right, so was that this one? Yeah. So 2x cubed minus 3x squared minus 12x. All right, got it? All right, so let's try graphing that now. So if you click on that link that's in the instructions at the top, you get this screen, which allows you to make a graph, okay? So let's see if we can graph this one. So what was it? 2x squared, let me see if I can get the 2x cubed. Ooh. All right, so 2x cubed what? Minus 3x squared. See if I can find the minus 3x squared, and then what? Minus 12x. Yay. Okay, so there it is on the screen. Let's close all of this. So you got a really not great graph of this, right? Because it's cut off on the top and the bottom. You can squeeze this a little bit though on the screen in Desmos, right? It's got a way that you can magnify or in this case reduce, right? Okay, so there's the picture. Can we from that one tell which was the right one? All right, y'all look at that because I'm going to have to switch back. So was it that one? Think maybe this one or this one. What? This one? Pretty close, right? Let's see. So this goes up to a little bit less than 10 right here and down here to minus 20 at this point. Let me give you a trick about Desmos. You point right here. I think it'll tell you what this point is. So minus 1 and 7 is this point. Someone write that down. And this point is 2 and minus 20. So Desmos is pretty good at picking out these peak and valley points. What are those called again? Turning points, right? Okay. So Desmos has picked off the turning points for us. And so we can answer questions already here, right? About increasing and decreasing. Where is this curve increasing? Negative infinity to -1, and then Jad again from what? 2 to positive infinity, right? Okay. 2 to positive infinity. It's increasing. So it's increasing on 2 intervals and then decreasing where? Well, between the 2 turning points, right? Which is -1 to 2. Okay. See that? So which was the right graph there? Was it the second one? Was it this one? No, right? It was this one, isn't it? Yeah, I think it's this one. Okay. Oh, that's terrible because part of this graph is cut off. Really can't tell where it switches from increasing to decreasing, right? Okay. So I would say this is not a good graph, all right? But I think it's the right answer. Where was it decreasing? See if I can type this in. So -1 to 2, right? And I'm looking for, am I going to find them? So let's try the square brackets and see if it will take them. So -1 to, where's the comma here? -1 to 2. And then what about increasing? Negative infinity to -1. And then combined with the other piece, which was what? 2 to infinity? So you've got 2 intervals there. The way you combine those into one set is by using a U, right? Okay, you use a union symbol, which is that little stylized U. You'll have to get that out of the palette, though. All right, along with the infinity symbols, you'll have to get out of the palette. Okay, so let's not try typing those in. Just a warning. Let's just check this and see what happens, since that was our goal here. Did it grade it right? Yep. So so it took square brackets. All right. So I'm not sure if it's going to take the parentheses or not. So you can experiment with that. Okay. What now? Yeah. All right. All right. So that problem already is a good lesson there. Let's switch back to a notes. And that's really it for increasing and decreasing. Okay. That's really all you have to know. All right. It's really just a matter of terminology at this point. Let's try one. So here's one that's just, I don't have a formula for this one. So let's determine where it's increasing and where it's decreasing. Okay. So so just all you have to do really when you're looking at the graph is just scan from left to right. Okay. and just see what the curve is doing, right, as you're scanning from left to right. So as we're here on the far left, right, and we start scanning across, what's that curve doing? Decreasing, right? It's going down, right? Okay, as x gets larger, the y values are following, right? So this function f at first is decreasing, right? We would say f is decreasing on, or you can say over is also appropriate. And let's see, what's that interval? Starts at minus infinity, I think, right? And goes up to, where does it stop decreasing? 2, exactly. What about this piece? It's not changing, right? Okay, so that's neither increasing nor decreasing. Okay, well, a curve that's neither increasing nor decreasing is said to be constant. That makes sense, right? Okay, as you move from left to right over this piece of the curve, the y values are staying constant, right? They're always 1. So so there is a third possibility for increasing and decreasing, and that is that a curve is constant, but that doesn't really happen that frequently. So I doubt if in the homework you will have a situation where your curve is constant. And then finally, here on the right, obviously, it starts going up, right? So f then is increasing on 5, starting at 5, right up to infinity. Now, one mistake that you're going to be tempted to make is make sure you're always giving your intervals in terms of the x-axis, not values on the y-axis. We're really not paying attention to values on the y-axis, okay? Give your answers in terms of the x-axis, right, okay? It's kind of tempting, like, for instance, on the right-hand side, if you're not paying attention, you might say, oh, f is increasing from 1 to infinity, because, here, the y value is 1, right? And then the y value goes up to infinity. So you might want to say, oh, f is increasing from 1 to infinity. That description is kind of correct, but it doesn't, unfortunately, match our terminology, all right? So you have to give answers there in terms of the x-axis. These points now here are not turning points, okay? They certainly are, important points on this curve, but they're technically not turning points. Turning point is only where a curve switches from increasing to decreasing or vice versa, okay? So it's got to switch from increasing to decreasing. So these 2 points at 2 and 1 and 5 and 1 do not count as turning points. All right, I'll let y'all try one here. Okay, so just on your own. Oh, it looks like I cut off part of the y-axis here. Let me put that back in. So this must be 1. All right, so take a look at that curve. Right, and see if you can write down where it's increasing, where it's decreasing. Just give it your best. Eyeball it there as best you can. Okay. Okay, so we're all able to write that out pretty quickly. When you have a graph, if the graph is kind of clear, then it's pretty easy from the graph to give a good estimate of where a function is increasing and where it's decreasing. Okay, so that's again one of the advantages of graphs is we can answer questions like from a graph, where is a function increasing, where is a function decreasing, pretty easily. At least give a reasonable estimate. Someone online there, can you tell me first where is it decreasing? I think that's the easy part. Can y'all type that in for me? Someone chat that in for me online. Some of the Zoom people, where is it decreasing? -2 to 2. I think that's right? Okay. Because on the pretty clearly, right, as you move from left to right, at first it's increasing, right? And until you hit this turning point right there. And then it begins decreasing. Okay. And it continues decreasing until you hit the second turning point, which is about right there. Okay. So so you're right, decreasing from -2 to 2. Okay. All right. And again, be careful that may be expected to use square brackets there, Mohammed, instead of parentheses, right? In giving your answer. So let me write that down here just for the note. So it's decreasing on, and I'm going to use the square brackets here, -2 to 2. All right. So then the other possibility, right, is that it's increasing. So let's see where it's increasing. Well, it's going to be increasing on the rest of the domain other than -2 to 2. So this domain begins at -infinity, right? And then, so it's increasing up to hitting the -2, right? And then again, starts increasing at 2. And apparently that continues all the way out to positive infinity. And remember, you combine these two intervals with the union operation, right? Union is how you combine two sets. These are sets, and you indicate that with that union symbol, that little stylized U, all right, which is not quite really a U, right? So you have to pick that proper symbol off of the palette and off of the palette there in WebAssign. Now, so we do have two turning points here, right? Okay. We have this turning point here at -2 and -1. This is a proper turning point because it switches from increasing to decreasing. And then the second turning point here, right, at what is that, 2 and -3, right? Because there the curve switches from decreasing to increasing. Now, there are really two types of turning points, right? You have a turning point where a curve switches from increasing to decreasing. I like to informally call that a peak turning point. Okay. And then you have this second type of turning point, right, where the curve switches from decreasing to increasing. I always call that a valley turning point. Okay. But of course, that's just informal terminology. The correct terminology for this in mathematics is this point would be called a local maximum. Because at that point, the curve reaches a maximum y value, right? At least in this region. Okay, of course, over here, it eventually gets a higher y value. But in this area, the highest y value is at this point, correct, right? And this type of turning point, this valley turning point, this is called a local minimum. Now, really, all right, when you say local maximum, that actually really refers to the y coordinate. And if you say local minimum, that really refers to just the y coordinate here, okay? But in formally, that's what's correct. But usually we refer to the whole point as a local maximum or the entire point as a local minimum. So in your homework, all right, if you are asked for a local maximum or a local minimum, that means either a peak turning point or a valley turning point. Be careful to see what they're asking you for. Are they asking you for the coordinates of a point, or are they asking for just the y coordinate? All right. So look at how the answer is formatted. Make sure you understand what you're really being asked for. Okay. So local maximum means a peak turning point, but really local maximum is the y coordinate of the peak turning point. Local minimum means a valley turning point, but really local minimum is actually the y coordinate of the Now, look, if you have graphs, it's pretty easy to, again, determine where a curve is increasing and where a curve is decreasing. It's also can be fairly easy to pick out if the graph is well made, where the turning points are, right? Okay. But that's if you have a graph. If you don't have a graph, then things are not always so easy. All right. Let me ask you this question, though, where you don't have a graph. All right. So where is this function? Its domain is all real numbers. Where is this function increasing? Where is this function increasing? So there's the function y equals 0.2x plus 7. And then same question. Where is this function 7 minus 0.2x? Where is it increasing? Okay. So, but I'm not going to give you the graph. Okay. So we're just going to work from the, all right. So things now become a lot more confusing, right? Okay. If you're not looking at the graph and you're just looking at the formula, see if you can answer the question without looking at the graph. And then we'll take our break. It's not hard. It's kind of a trick question. The way to do it is to visualize the graph in your head. Without actually drawing it. So can y'all visualize those graphs? 0.2x plus 7, 7 minus 0.2x. Can y'all visualize those in your mind without actually drawing them? Enough to visualize enough to answer these questions. Okay, let's see on the first one. All right. Someone at home, do you know, or wherever you're at, someone on Zoom, for that first one, do you know where this one is increasing? Can someone answer? Has that confused you? Zoom people, y'all scared to answer me? All right, well, let's try it in the classroom then. Okay, so who has a bright idea to answer that question here in the classroom? Where is y equal 0.2x plus 7? Where would that be increasing? Yeah. Why do you say all real numbers? Why is it going to increase forever though? When you graph that, what do you get? It's a straight line, right? That's the graph of a straight line, right? Okay. Yeah. 0.2x plus 7 is the graph of a straight line. What's its y-intercept? 7. But more important, what's its slope? 0.2, which is positive, right? Not a very big positive number, but that's positive. So that tells us what about the line when we graph it? It's increasing, right? Yeah, it's increasing from left to right. But lines don't have turning points in them, right? Okay, lines are straight, right? They don't have any turning points. They don't have any wiggles in them. So if it's increasing in one place, it's always increasing, right? Okay, I mean, that's what we kept stressing about straight lines, right? The slope is steady on straight lines, right? So this line is always increasing from minus infinity to positive infinity, right? So see, this one is a simple enough curve that you can think about it just in your mind, right, and figure out where it's increasing or where it's decreasing, right? So it's increasing there from all real numbers, right? You can write that down as an interval minus infinity to infinity. What about the second one? Not increasing, right? It's never increasing, right? Okay, there's no place where it's increasing. It's always decreasing. This also is a straight line, right? Except its slope is what? Yeah, negative, right? Okay, so so the answer is it's just never increasing, right? No place where that curve is increasing. Okay. Well, all right. So see, we could answer questions about these two curves just because they were simple curves, right? Okay. Their graphs are just straight line. But in general, it's going to be hard, okay, to without some prior knowledge of what the curve should look like, it's going to be hard to answer where a function is increasing or where it's decreasing without actually looking at the graph. Okay, that's going to be now a big topic in calculus. All right, how can I figure out where is this curve increasing, where is it decreasing, just from the formula without having to look at the graph? Okay, how do I figure that out from formula? Unfortunately, though, we're stuck here in pre-calculus, so we don't have the tools of calculus, so we're going to have to graphs, all right, okay, to tell where a curve is increasing or where it's decreasing. So we're going to have to be sort of chained to our calculator, some graphing device to help us make graphs, unless it's a curve where we really understand what the graph is looking like, right? Okay, like a straight line. Okay, all right, so let's take a break here and we'll come back and we'll look at one and we'll make a graph of it and answer where it's increasing or decreasing from the graph, okay? Function direction, yeah. I always call increasing or decreasing the direction of the function. Hang on a second. Let me see if I can stop the. Okay, let's start again. So you might see problems like this one in the homework. And so there you're just given a formula for a function, obviously not a straight line, right? And then just ask where is it increasing, where is it decreasing, right? And what are the local maxima and minima? Maxima is the plural of maximum, minima is the plural of minimum, right? So so we have no idea what x cubed minus 8x plus 1 is supposed to look like. That's not one of the curves that we've studied in class, right? Other than we know it's not a straight line. So so we're kind of in the dark here, right, about how to answer this question without actually making a graph. And so that's what we have to do. And so, but to do that efficiently, we'll have to use some sort of graphing device, right? So remember, in the homework, like I was showing you guys, right? You know, in that function direction homework, right, at the top of the screen, you have a link to this screen, right, that can help you make graphs, or you can try using your graphing calculator as well, right, to build a graph of that. I think I have a graph of this one already drawn, however. And once you've got the graph, as long as you've got it, that's not the one. As long as you've got a decent graph, then it's not really that hard to answer the question, okay? Or at least give a decent estimate, a good enough estimate, you know, to get a decent answer, right? So so here I just typed in that formula, x cubed minus 8x plus 1, right? And there's the graph that it made. And so that's a good start, but that's not really, you know, that graph's not really enough, right, to completely answer the question, because the top of the graph and the bottom of the graph are cut off. So and those are going to be the turning points, right, on the graph. So we're going to have to adjust the graph somewhat And that means we're going to have to change the graphing window. So the graphing window is the portion of the X and Y axis that you're seeing in the graph, right? Okay. And so, so we need to adjust those. One way, again, in this program, which is called Desmos, is, you can just enlarge or decrease the picture. So you can zoom in or zoom out. If we zoom out then a little bit, then that already gives us a fairly a decent graph, right, of this curve. I think it's enough there to answer the questions that we need to answer. But it's still not great, still not a great graph of that curve, because notice the graph is kind of compressed from left to right, okay? Because there's these lots of white space there on the left and on the right. So you could make the graph fill the screen up a little bit better if you cut down on the portion of the x-axis that you're graphing. I always call that the x window. So if we cut down on our x window, could make a little bit better and graph, in the sense that it'd be more useful for answering the questions that we want to answer. You can do that in Desmos by hitting the wrench here and changing the portion of the x-axis that's being graphed. Of course, you can do that on your graphing calculator as well. Let's see. I think for the x-axis, we really don't need anything more than -5 to 5, right? Okay, because you really can't see any of the curve outside of that portion of the x-axis anyway, right? So I'm going to go hit this, and let's see if I can change that. So let's change this to -5. Okay, for the left side of the x-axis, right? And then for the right side of the x-axis, let's change that to 5. Okay, and so that's better, right? Same graph, but now we can see it a lot nicer. Okay, and that's really where all the action is on this curve anyway. I don't think anything of interest is happening on the far left, or anything is happening on the far right. I'm not sure of that, but that's what seems to be the case, right? It looks like on the far left, graph is just continuing to decrease, right? And on the far right, it's just going to continue to increase. Where the graph is wiggling here, right, where it's changing a direction, is here in the middle, okay, that we can see. So let's see, where does it change direction? Woo, wow. Right here at this point, kind of. And so there's our estimate for that. All right. And y'all write that down. You want to write that down for me? Okay. -1.63 and then 9.709. And then here's this other turning point at 1.63, and then -7.709. Okay. All right, now, so can we write things down now? Let's see if we can do it here. We did have a local maximum. And what were the coordinates of that local maximum? So that was the point on the left, right? The turning point on the left was the local maximum. This one. So there are the coordinates: -1.63, -1.633, and then 9.709, right? Now, those are almost certainly not the exact coordinates of that turning point, okay? All right, those are decimal approximations for that turning point. So you see, in calculus, you will learn techniques for determining what the exact coordinates for that turning are, okay? Not just decimal approximations. So this is a peak turning point, right? Remember, but really, technically, the local maximum is really the y coordinate of the point, okay? It's not the entire point. Let's see, what about the local minimum? There was a local minimum too, right? And that, I think, was at 1.633, and then something like -7.709. Is that, am I recalling that correctly? Right here, yeah, 1.633 and then -7.709. So where is the function increasing? So from minus infinity to minus 1.633. And then is it again from 1.633 to infinity? Right, and remember you combine those with the union symbol, right? Yeah, so from minus infinity to minus 1.633, right? This part of the graph, right? It's increasing, and then again, starting increasing here at 1.633, and apparently that's going to continue to infinity. Unless we're getting fooled, and there's some more turning points further over here on the right, or more turning points further on the left. It doesn't look like there are, but you know, we don't have the tools for deciding that perfect, okay? That's another thing we'll learn in calculus, though, right? How can we be sure that there aren't any more turning points on the right or aren't any turning points on the left, even though it certainly looks like it's not, right? And then let's see, decreasing between, right, the two turning points, right? So just a matter there of making a graph of that curve and then, you know, giving estimates, right, from the graph. So don't quite get exact answers there. All right, now look, once we've determined that a curve is increasing on an interval or decreasing on an interval, then we want to apply the same idea to the curve that we do to straight lines. And that is, we want to measure how fast the curve is increasing or how fast the curve is decreasing, where it's increasing or where it's decreasing, right? What allows you to give that measurement for straight lines? So if I ask you for a straight line, how fast is this straight line increasing? Or how fast is this straight line decreasing? You would say, oh, that's the same as what? That's the slope, right? Okay, the slope for a line is a measure of how fast the line is increasing, right? Or how fast the line is decreasing, right? Well, for curves, of course, things are more complicated because the curve is not always increasing and the curve is not always decreasing. And it's even when it is increasing, it's not always increasing at a steady rate, or even where it is decreasing, it's not always decreasing at a steady rate. So asking how fast the curve is increasing or how fast the curve is decreasing, unfortunately, that's a more complicated question than it is for straight lines, okay? But we're going to try to answer that question just like we do for straight lines, okay? But when we do this, oops, I'm sorry, I cut y'all's chat out. When we do this, we just have to keep in mind, we just have to keep some caveats in mind, some warnings in mind, that curves are not straight lines, all right? Let me show you what I mean, okay? So to measure how fast the curve is increasing or how fast the curve is decreasing, we're going to calculate for that curve what's called the average rate of change. This is going to look very familiar to you, though, because the average rate of change is just the slope. The formula for the average rate of change is just the slope, all right? In other words, we're going to treat the curve, to answer this question, we're going to treat the curve like it's a straight line, all right? So let me draw you a picture there, all right? So here's a function named f. I don't know what the formula for this function is. It's not important, right? It's just for this picture. And obviously, we can see f is what? Is it increasing or is it decreasing? Yeah, clearly, right? It's increasing. Okay. So if we want to measure how fast the function is increasing, right? The rate at which that function is increasing, okay? Again, what makes that tricky is that rate of increase is not always steady, right? Okay. If you'll notice here on the left, at first, the function is going up rather quickly, right? Okay, see, it's almost vertical here on the left, right? It's going up very fast. But as you move further to the right, the curve starts to flatten out, right? It's not going up as fast. Okay, so that rate of increase is not steady for a curve like it is for a straight line. Okay, so when I ask how fast is the curve increasing, I'm going to have to tell you specifically what portion of the curve I'm interested in. Okay, so I'm gonna when we ask this question, what's the rate of change for a curve? We will say from a given x value to a second given x value. We have to be very careful about where we're asking how fast the curve is increasing or how fast the curve is decreasing. You don't have to do that for straight lines, right? Because for straight lines, the rate of increase or decrease is always steady. Okay, so it doesn't matter where you start, observing the straight line, right? Okay, or where you finish observing the straight line, because that rate of change is steady between any 2 points. But that's not the same for curves. So we have to indicate between which 2 points are we interested in measuring how fast the curve is increasing, or what the rate of change of the curve is. All right. So in this picture, I've indicated I want to know what the rate of change is between these 2 x values, starting at x equal a and finishing at x equal b. Okay. All right. So how do we measure how fast the curve is increasing from x equal a to x equal b? It's so easy. We treat the curve like a straight line. Okay. So what we do is draw a straight line between these 2 points on the curve, the point at x equals a and the point at x equals b. Notice the curve is not a straight line, right? But I've drawn a straight line connecting these 2 points on the curve. I'm going to treat the curve like it is a straight line. That's this purple line here, by the way. That's called the secant line. So if you connect 2 points on a curve with a straight line, that line is called the secant line. And so it's like the trig secant, right? Okay. And all you do is calculate the slope of that line. Okay. So for this function f, we would say, oh, the rate of change, okay, the rate of change, but for this function, or how fast this function is increasing from x equal a to x equal b, it's the slope of this line. And how do you calculate the slope of this line? You just use your slope formula. All right. So all this rate of change formula is just the slope. So it's this y coordinate here, right, which is f of b, minus the y coordinate for this point, which is f of a, and then divided by the difference of the 2 x coordinates, right, b minus a. It's just the slope formula. Now, you might be wondering, why do you put average? Why don't we throw in the word average here? Why not just call this the rate of change from a to b? Okay. And the reason we do that is we have to be very careful to make it clear that the curve is not a straight line. All right. Okay. If I said, oh, the rate of change of this curve from a to b is this quantity, I would be sort of implying that that rate of change is steady, right? Okay. It's always the same anywhere here from a to b. But if the rate of change were steady, the curve would be this purple line, but the curve is not the same as this purple line. Okay. So the way we really want to clarify that this is a curve and not a straight line is we throw in that word average. All right. Okay. This is what happens on average from a to b. This is how fast the curve is increasing on average from a to b, but it's not steady. Okay. It's not a steady rate of change from this point to this point, because if it were steady, you'd have a straight line. Okay. So again, what's the purpose of average rate of change? It's like the slope of a line. Okay. It gives us a measure, a way of measuring how fast the curve is increasing or decreasing from some point on the x-axis, from some value on the x-axis to a second value on the x-axis. All right, let's just do it. Let's just use the formula. The formula is really easy because it's just the slope formula. So here I have a function which is not a straight line, x minus 3 squared. There's the graph of x minus 3 squared. Okay, so you get a curve that looks like this. It's not a very complicated curve, but it's not a straight line. right? So it's not always increasing or always decreasing. In fact, you can tell what it's decreasing at first, right? From where to where? Yeah. Yeah, this is 3, right? Yeah. So it's decreasing from minus infinity to 3, and then it's increasing from 3 to infinity. Okay. So what I want to calculate, though, is what's the average rate of change of this curve from x equal 1 to x equals 3. Okay. So on average, how is this curve changing from x equals 1, which is right here, right? X equals 1 is right about there, right? To, if I can get it to draw for me, from x equals 1, yeah, right about there, right, to x equals 3. Well, without even calculating that average rate of change, you can already tell me, is that average rate of change going to be positive or is it going to be negative? Yeah, it's going to be negative because from x equal 1 to x equal 3, this curve is falling, right? Okay, this curve is decreasing. So the rate of change has to be negative. What the average rate of change tells you is how fast is that curve decreasing from x equal 1 to x equal 1, right? Okay, that's what the average rate of change is trying to indicate. Remember, that average rate of change is going to be the same as the slope of this line. You're just going to treat the curve as a straight line, kind of, and just calculate the slope of that straight line. Again, that straight line is called the secant line. So what's that going to be? Average of change. Unfortunately, we don't have a, this is kind of a bad thing in mathematics. We don't have a symbol for this, okay? We don't have notation for average rate of change. Just have to write it out. So how do we calculate that average rate of change, though? Remember, it's the same as the slope formula. So you calculate f of 3 minus f of 1. Those are the two y values that match x equal 1 and x equal 3 on the x-axis. So this is the same as y2 minus y1 over 3 minus 1, the difference in the two x values. What is f of 3? Well, it looks like, yeah, it looks like f of 3 is 0, right? But if you want to be sure of that, of course, you can plug it into your formula, correct? So you would have what? 3 minus 3 squared. That is going to turn out to be 0, right? Minus, and then we want f of 1, which looks like it's 4, but let's be sure of that by plugging it into our formula. So we have 1 minus 3 squared, which indeed is going to be 4, correct? All of this over, well, we can all do the denominator pretty easily, right? That's 2, right? So what do we end up with in the top there? 0 minus 4, correct? Over 2, which turns out to be minus 2. So you get a pretty easy value for that average rate of change. What is that telling you? So what is our interpretation of the minus 2? So keep in mind, this is kind of like slope, right? So what is that minus 2 telling you? Decreasing by 2 when what happens? By 1. Exactly right. Don't forget about that. Okay. So this tells you that y is going to go down by 2 when x goes up by, right? Now, all right, so let's write that down. So on average, from x equals 1 to x equals 3, what'd y'all just say then? Huh? The y value, or you could say the function, decreases, right? Yeah, decreases, am I spelling that right? Decreases by 2 because our Average rate of change is -2 here. When what? What happens? When x increases by 1, right? Why am I so this is the part that students always want to leave out and then they get counted off, right? Why am I so careful of putting here first from x equal 1 to x equal 3? Why do I have to bother to put that phrase in my interpretation? Right, because this is what happens from x equal 1 to x equal 3. Over here, from x equal 3 to x equal 4, something completely different is going on, right? Okay. In fact, on the left-hand side here, what's happening to the curve? I mean, on the right-hand side, what's happening to the curve? It's increasing, right? It's not even decreasing, right? Okay. So you have to be very clear that you're talking about from x equal 1 to x equal 3. That's where the curve is decreasing. If you leave that off, then you're being misleading. But why the on average? So why not just say from x equal 1 to x equal 3, the function decreases by 2 when x increases by 1. That means it would be a straight line. That means it would be steady, right? It's not steady though. Is in fact, does it always go down by 2 when x increases by 1? No. Look, here's 1. At first, when you go from 1 to 2, how much does it go down? Well, let's calculate it there. You started at what? 4. And where are we at 2? On the curve, not the line. No, on the curve, where are you at? Looks like what? I think it's 1, isn't it? Okay, I think it's exactly 1. All right. So you've gone from 4 down to 1. That's a decrease of how much? 3, right? So you actually fell more than 2. Now, from 2 to 3, how much do you fall? 1, right? Okay. Well, first you fall 3, then you fall 1. That's an average of what? 2, right? Okay. That's an average of 2. But you weren't always falling by 2, see? Okay. That's just what happened on average. So the on average there is very important in the explanation. That's what I was saying. This idea of measuring change, increase or decreasing for curves it's just messier, right? It's a little bit more cumbersome than it is for, it's clumsier than it is for straight lines, okay? But that's just the way it is. Let's try another one. Y'all do one for me really easily. So really easy. You want me to write the formula down? I want to know what's the average rate of change between 4 and 7. And write down your explanation for that also. Here was the function, I forgot, it was x minus 3 squared, was it that? Yeah. So there's the formula. So x minus 3 squared. So what is the average rate of change from 4 to 7? You can see from the graph it's going to be positive, right? Okay, because that curve is increasing from x equal 4 to 7. But how fast is it increasing from x equal 4 to 7? That's what we're trying to answer this question. Okay. Not just it. How fast. Calculate here while I have keep going. What's the form? Now, actually, there it is, right? So it's just as slow. I mean, there's the formula for the function. So you're all good at slope. So there's your formula, f of b minus f of a over b minus a. I think this is the b, right? This is the a. All right, let's try it here and see what we wrote down. Okay, so this one should be fairly straightforward if you just have to remember the formula, right? So there's the formula. Let me recopy the formula. So f of b minus f of a for b minus a. So here the smaller x value is 4, so that's the a. The larger x value is 7, so that's the b. So we have f of 7 minus f of 4 over 7 minus 4. So the denominator is really simple, right? That's just 3. And in the numerator, we have to do just a little bit of arithmetic because we have to plug 7 into our function formula. So I have 7 minus 3 squared minus, and then 4 minus 3 squared. So that comes out to be 4 squared, right, minus 1 squared over 3, which looks like 16 minus 1 over 3. Is that 5? Right, okay. So get an average rate of change of 5. So how do we interpret that? We would say on average, and that's really important because this rate of change is not steady, right? On average from x equal 4 to x equals 7. You could say the function f, or you could say the y value, or y increases, right? Because this is positive. So increases by 5 when x increases by 1. Remember, in average rate of change, just like in slope, the x value is always increasing by yeah, right. Yeah, that was the same. That's the same one. Well, let's continue with it again. Okay. All right. So let's see if we can get this part. All right. So now we want to find the average rate of change, except they're going to ask you not for a they're going to ask you here not for not between two specific values, but between two variable values. All right. So we want to find the average rate of change from a to a plus h, but they're not going to give us specific numerical values for a and for h. All right. So this is going to require some algebra. Let's see if we can gut through it. Okay. So wow. So, but the first part of getting this correct is you've got to write it down properly. Okay. So we want to calculate this average rate of change, right, between these two values. So this is the B value, this is the second value, and the A value is A. Okay. So this is what you're going to plug into your formula, or your average rate of change formula for B and for A. So for B, you'll plug in A plus H, and for A, you will plug in A. Okay. So what's that going to look like? It's going to look like F of A plus H minus F of A over A plus H minus A. Let's see, for B, I plugged in A plus H, and for A, I plugged in A. We've already done this sort of calculation before. What is this? What do we call this calculation earlier? We've already seen this calculation. F of A plus H minus F of A over H. That's a difference. Yeah, all that is a difference quotient. We did that. So when you're computing difference quotients, that's really an average rate of change. That's where difference quotients come about, all right, is in computing average rates of change. All right, now let's see if we can calculate this difference quotient there. So this is going to take a little bit of effort, because to calculate F of A plus H, remember the formula for F is x minus 3 squared, right? So you have A plus H minus 3, don't forget to subtract the 3 off of that, squared, minus, and then you have A minus 3 squared over H. Yuck. Okay. So now I have to square A minus 3. That's hard enough, but this one is really bad. Okay. I have to square A plus H minus 3. Okay. All right, let's do those. We just have to be patient about it. Okay. We have just enough time to do that. So let's see if we can do it. So let's start with the A minus 3 squared. That's the easier one. So remember, when you square that, that means you multiply it by itself, right? That means A minus 3 times A minus 3. So what do we get? We get A times A is A squared, right? You're going to get minus 3 times minus 3 is what? 9. I'm leaving some space because remember, you got the terms in the middle with what? A times a minus 3 is a minus 3A. Minus 3 times A is a minus 3A, right? So add the two minus 3A's together, and there it is. Oh, so that's not bad. Okay. So that's the A minus 3 squared. Now, the other part is, see how bad this is. That's A plus H minus 3 squared, which means you take A plus H minus 3 and multiply it by itself. Okay, guys, you know how to multiply this by itself? A plus H minus 3 times A plus H minus 3. You have to take every term in the first parentheses and multiply by every term in the second parentheses. You just have to be patient, but it's not hard. You just have to be methodical about it. So let's do it. Let's start with the A, multiply it by everything in the parentheses. So we get what? A times A is what? A times H is A times H, right? A times minus 3 is minus 3A. Now I'll start with the H. So you have H times A. Let's write that as A. I'm going to put the A first. Just keep them in alphabetical order. What's H times H? H squared, right? And then you have H times the minus 3. So that's minus 3H. Now the minus 3. So you get what? Minus 3A, right? Minus 3H. Minus 3 times minus 3 is positive 9. Are there any like terms there that we can add together? I see a couple of AH's, right? So that's 2AH, right? Are there any other like terms? I don't see any. So these two are gone, right? So I have minus 3a plus h squared. Oops, we have h's, right? So minus 3a plus h squared, and then this minus 3h and this minus 3h, that's minus 6h, right? And then this these two. Oh, so I messed that up, right? Minus 3a and minus, this is supposed to be minus 6a, right? And then plus 9? Oh, that's not as bad as I thought. Now just put those in. So you have to rewrite a bunch of stuff, but a squared plus 2ah minus 6a plus h squared minus 6h plus 9. And then we're subtracting off, and be sure you subtract off the whole thing. So I'm going to put it in parentheses. We're subtracting off f of a, right? Which was a squared, which is a squared minus 6a plus 9. All of that divided finally by h. Be very careful now that you put that second, the f of a, right? Make sure you put all of that in parentheses, because you're subtracting all of that. And when you get rid of the parentheses, what happens here? When you distribute the parentheses, what happens? Yeah, the signs change, right? So this becomes, I'm not going to rewrite it, but let me just erase the parentheses. This becomes minus a squared. This becomes what? Yeah, plus 6a and minus 9. Now the reason that's important is what cancels now. Let's start looking. Yeah. So this 9 goes away, right? The 6a's go away. Ooh, that's beautiful. And the 9's went, and the a squares went away. Wow, what's left here? Not much. 2ah, right? Plus an h squared minus a 6h. Is that it? This, and this, everything else is gone. All of that divided by h. And that's nice because look, every term in the top has an h in it. So guess what? You can divide out the h in the denominator. So what do you get left with? 2a plus h what? Minus 6. Ooh, that was terrible, but it just boiled down to not bad at all. 2a plus h minus 6. There's our average rate of change from a to a plus h. Okay. Really the same as the difference quotient. All right. So just a little algebra. Okay. Well, that's really all there is about function direction. All right. Increasing, decreasing is really a pretty simple idea, except you have to have what? Given a function and you want to determine where it's increasing, decreasing, you really need to have what? You really need to see what? A graph. Okay. Yeah. All right. Really need to see a graph. Okay. So and really cannot do without the graph until you get to calculus, when you start learning to answer these questions without having to rely on graphs in front of you. Okay. All right. So I'll see you guys on Wednesday. All right. You guys at home, I'll see you on Wednesday also.